Lab 4 oscillation. So the purpose of this lab is to analyze the motion of an object that is swinging back and forth while also oscillating on a spring and understand how kinetic, gravitational potential, and spring potential energy change. So the physics principles I used are the energy principle and the momentum principle, which are shown right here. And then some of the formulas I used are the velocity update, position update, gravitational potential, spring force, kinetic, and then period of oscillation and spring stiffness. So a quick preview of my results. The data in my computational model was slightly different than my experimental data. And in the computational model, the total change in energy of the system was roughly 0, but not exactly 0. So the initial conditions of my experiment, so the system is the mass, the spring, and the earth, and the system has no surroundings. And so my initial x and y coordinates are shown here, and the mass is 0.402 kilograms, and delta t is 1 over 10.5. So here's my tracker data. You can see each point is where the spring was at each frame, so this is kind of the path of oscillation. And then here you can see the oscillation in the x direction, the oscillation in the y direction, and then the coordinates at each time interval. So here's my tracker analysis. I calculated t, which is the period of oscillation, to be 1.504. This is my calculation. So I took the equation for t and I rearranged for k, which is spring stiffness, and I plugged in t and m, and I got k to be 10.552 newtons. So here's my computational model code. So I put in my ball mass, initial position, initial velocity, which is obviously 0, delta t, and then the gravitational constant, spring constant, L vector, and then my equations for kinetic energy, gravitational potential, spring potential, and total energy. And then over here is where I used velocity update and position update, as well as net force and spring force and force of gravity to update to get delta K, delta U, G, and delta US, and then the delta E as well. So here's my analysis for my computational model. This is all the energy showing how all the energies are changing frame by frame. So there are a couple errors here that I'll touch on later, but I'll just say right now, obviously kinetic energy can't be 0, or it can't be negative like it's shown to be in some of these, and change in energy is not constant, or it changes. I guess frame by frame, energy does not remain constant. So comparing my results, this is my tracker video. As you can see, the oscillations are much more uniform than they are in my computational model. But they're still pretty similar. It oscillates, I guess, slightly more in the model. So potential errors in my experiment are improperly placing the center of mass in the tracker video, maybe some external factors like air resistance or imperfections in the spring, or errors in calculating my variables like t and k. So what does it mean? My model does not satisfy the energy principle because energy does not remain constant. Frame by frame total energy is changing, and obviously kinetic energy can't be negative, like I said earlier. And the second part of the what does it mean? So the oscillation period in the x is slightly longer than the oscillation period in the y, which could be explained by the man in the video releasing the mass with slightly more velocity in the x direction, and maybe initial velocity not actually being 0. Or it could be explained by an error on my part, like incorrectly placing the center of mass.